I guess the stage is mine now. Sorry, I don't speak Russian, so I stick to English because I guess most of you don't understand German. My name is Christoph Dietzel and I'm with DKIX and Technical University of Berlin. Today I'd like to talk about detecting peering infrastructure outages. So basically the idea is there are outages on the internet and we'd like to detect those and get some insights on where and when they happen. This is a joint work with Vasilis, Georgios, Anya, Arthur and Emil. So first of all, let's talk a bit about what is a peering infrastructure basically, like sort of a definition. So as we all know, those are critical to our internet ecosystem and we really heavily rely on internet infrastructures. So this is why we have SLAs. So regardless whether it's an ISP, an IXP or some other operational entity on the internet, we assure a certain uptime within our SLAs. So if we talk about internet exchange points as one of the two peering internet infrastructures I'm talking about, we talk about shared switching fabrics on layer 2, and most ASs facilitate bilateral or multilateral peering at IXPs. The largest IXPs in the world support more than 100,000 peerings and have a peak traffic of about 6 terabits per second. So typical IXP SLAs, in this case, I have a reference as AMSIX, the big exchange in Amsterdam, and they have an SLA of 99.99% uptime. That means they may have a downtime of about 52 minutes per year. If we focus on the other peering internet infrastructure, which is carrier hotels or so-called carrier-neutral colocation facilities. And those infrastructures are physical colocations to, as you all know, to get your gear there and to interconnect with other ASs and have PNI cross-connects, for instance. So those facilities, even though they are not different from the IXP ones, because usually IXP hosted in the same facilities, they support about 170,000 of interconnections within one such a carrier hotel. So typical SLAs here have 3 nines, which means the SLAs are quite stricter here. So they allow a downtime of about 5 minutes per year. So now we really know that the downtimes for such crucial facilities to have a flawless operation of the internet are quite strict. However, if we look or have the experience as an end user, sometimes we really notice services don't work, we can't really connect to the internet. I mean, all of us know it. You want to go on a website and somehow it seems to not work. So maybe you have a smartphone or something with a different provider and you just check on the internet. What's going on basically? No one's telling me. And the same holds true for an ISP operator. Because sometimes you see that a certain peering doesn't work anymore or certain peerings at the facility, but basically no one from the co-location facility is calling you or really like telling you right away what's going on. Because BGP sessions breaking down, you notice within sub-minutes or seconds. But no one tells you. And maybe you get a notification email after that, standard procedure, but actually the root cause remains unclear, especially if you don't really are in a contract relation with this facility, because it could just be one of your peers who has an issue with the data center operator there. And then you just may look it up on the internet, right? Like British Telecom outage, or there was an issue with Equinix outage, a lot of downtime in Zoho, or cooling issues in Australia, delayed flights. But this is just primary source of information nowadays if you really want to know the root cause of an outage. And if you're really affected yourself or you are sitting in your NOC and you are affected, basically what you're going to do is you just use the current practice, is anyone else having this issue? So you're sending out emails, you call in people and really trying to get to understand what's going on. So ASs typically try to crowdsource the detection and localization of outages. And we consider this as inadequate transparency and not the desired responsiveness from infrastructure operators. I mean, we all know that ISPs and IXPs and co-location facilities are busy fixing things, and the technical guys there don't really have the time to communicate and make a marketing statement where they apologize about the outage. But we believe that at the current state of the internet, which is very vital and crucial for our all daily lives, I mean, we are network operators, but if I consider my parents, my friends, they all rely on it not because they live from it, but because their services somehow rely on the internet as of today. So we defined our research goals to really, we wanted to learn 3 things. First of all, the first research goal is outage detection. So what we want is to detect an outage. This sounds very simple, but we want to have it on a very timely, fine granular level as possible, which means in sub-minutes we want to really know whether there's an outage somewhere or not. So close to real time as possible. Outage localization, so we want to really know where the outage is and not like the typical thing that you can tell the AES on the AES path which observed issues. We just really want to know the facility and want to pinpoint down to co-location facility what's going on. And we want to distinguish between cascading effects and the real outage source. Because sometimes you can't really tell because you receive a lot of different signals, you see a lot of BGP sessions breaking, and you can't really tell what actually the source, the root cause of this event might be. And the third point is outage detection, tracking, sorry. So we want to really track what's going on, meaning we would want to determine the duration until it's over, like recovery times, and we want to know the shifts in routing path. Where do the path go? How long do they stay there? Do they get back? And obviously the geographic spread to somehow infer a bit the impact of an outage. So therefore, we build a system which utilizes the risk collectors. So the next talk is going to be about the risk collectors, and we use those as one of the primary sources for our system. So we get all the BGP information close to real time again, and what we do is we map sort of the facilities on the internet, and we map the path that go through a certain co-location facility. I have here a toy example which sort of explains how our system works from the initialization to the monitoring and detection phase. So in this toy example, we have a lot of facilities here, which are co-location facility. One facility has an IXP, and we have a number of ASs. And if you see the green VP, the vantage point in the brackets, those are our information sources. So we got feeds from those ASs, not from the other ones we may observe. And in the plot, we observe actually time and the number of stable paths. Because what we do in the first place, we focus at one specific facility. In this case, it's facility 2. And then we just map all the paths that traverse the facility 2. And then we have a stable path set. So we monitor it for a certain duration, not considering those coming and moving all the time, but a stable set of paths. In this case, it's 20,000 different paths. So, and what we do basically is, we just don't focus on the AES path, but we really focus on the communities. So as you can see, all our vantage points, we observe the BGP announcement, we receive it and see that the AESs mapped the facility where they receive the prefix. So that gives us basically knowledge that not on an AES path, because it's clear that the packet will traverse this AES, no, a level below us. So we really get notion on which facilities actually were traversed for each given packet. So next, we really continue to track this for a longer time and really get a more stable set. And yeah, from here, we have the continuous monitoring phase. And then we might observe that there's something changes. So we see the AES path remains the same. It's still the same AES path. So if you just monitor AES paths, you won't really notice a difference. What changed is the community. So the path does not really traverse the facility 2 as before anymore. It does traverse facility 1. So we just see a change. And that's basically what we care about. We don't care about AES path changes. We care about facility changes. And then, again, we have an event, an outage signal. From here, we see, oh, like all or most of the paths that traverse facility 2 going away to other facilities at the same time. So we have concurrent changes of community values for the very same facility. And this is just an indication yet. It's not really an outage, because what could it be? It could be a partial outage. Sometimes there's like a big campus and there are several buildings, so power cut for a part of the facility. Or it could be depeering of a large AS. It could also be major routing policy changes, changed traffic engineering. So from here, we really need to dig a bit deeper to really get an understanding and to really have reliable metrics. So we start a signal investigation phase. So we do targeted active measurements, facilitating the RIPE Atlas system, and we try to distinguish basically how disjoint are affected paths. So are they completely disjoint, or is it a joint set, to really infer whether it's related or not. And we need to have a notion on how many AS links have been affected. Is it distributed across different ASs? Is it just one AS? And those things really help us to get better understanding of the situation. So, and after the signal detection and the deeper investigation phase, we continue to do outage tracking, which means we infer the end of the outage, like the time when most of the path moved back. Not in all cases all paths move back. So facility 2 is up and we continue the outage tracking. So I got an example here to really illustrate a bit the value of what we did. Because one could simply say, of course, you can just focus on the risk collectors, for instance, and see having a huge number using BGP stream, for instance, having also BGP mon and like a lot of BGP feeds. And if you just simply plot like the announcements, the withdrawals, and the state changes, you might get a notion of that something breaks. Of course, the point here is this is only AS level, and this is very loud. So you really see a lot's going on. And if you focus on the gray bar here, there was actually an outage of an IXP. But if we look at this plot, there are a lot of other outliers of a lot more announcements, and note this is a log scale. So we don't really see anything if we just plot everything we have. And if we apply the metric I just introduced to you, like focusing on the communities that annotate really the location, we really see what's going on, because then we can really see before we have a few changes or a few number of BGP messages, none to a few, and at the point we see that there are a lot of BGP messages, and the blue line also shows us that all paths moved away from that IXP at that time, which really gives us ground truth on, okay, something broke in this IXP and not in the neighboring facility or something like that. But again, outage localization is more complicated, and we really have a sophisticated system with a huge algorithm. But given the limited time here, I just like to introduce two corner cases to really illustrate you what the issue from here on could be, like how we try to limit the number of false positives. So as you could see so far, we really rely on the BGP communities that a lot of ASs tag the ingress routes with a location. But failures in intermediate infrastructures could also affect the near-end infrastructure path, meaning like there's some other co-location facility that's used by a customer of my customer, and my routing actually changes even if something breaks there. So basically, sometimes it's hard from my vantage point, because I have a limited view, to really understand what's going on. So here again, the toy example, but this time with a different scenario. So we focus on facility 4, because our system does track not just one facility, but each facility by itself. And in this case, we just look at the data set from the perspective of facility 4, and we see, for instance, all the path, like we have 2 paths in this scenario that traverse the facility 2. We see that in our vantage point, and they tag their ingress point. And then we just see that in this scenario, facility 2 has an issue and goes down, so it's out of service. And an outage in facility 2 causes a drop in path at facility 4, right? So from our vantage point, if we just have a single one, it would not make a difference whether, or it makes a difference, but we can't really distinguish whether facility, is it because of an issue within facility 4 or is it facility 2 in this case. And another scenario is we don't map all facilities. So you can see facility 3, and we can just map facilities where ASs tag the community or use the communities for the ingress tagging. Some locations might not have that. And if that's the case, that makes it harder for us to perform a proper detection. So an outage in facility 3, for instance, causes a drop in path at facility 4 again, as we can see here, because we don't have it on our map and we can't really distinguish. So our solution to that is, as I mentioned earlier, is to create really a high-resolution co-location map. Means mapping all ASs to facilities, ASs to IXPs, IXPs to facilities. And we use the sources, just public available sources, so you could also do the same and verify. PeeringDB, data center map, and operator websites. And by doing this, we can really monitor like a huge number of facilities across the globe and correlate the data to really get an understanding what's going on a global scale. And due to the decorrelation, the behavior of the affected ASs can be estimated based on infrastructure collocations. So outage source disambiguation and localization. So path not investigated in aggregated manner, but at the granularity of separate ASs and facilities, which means on the left-hand side, you can see what we did before, like very aggregated. So you just have this line and it goes up and down, and this seems to be your only metric. But if we prepare our data in a different way, like in the plot on the right-hand side, where we really have like each bar, we have a baseline for certain routes. And then we really see that they might change, go away, or they don't change. And we see, for instance, here we have 2 outages sort of at the same time or very close to each other at different locations. And if we really look at the first plot, we don't really see that actually those are different ones. In the right-hand side, we can really see what's going on for each set of path that we have. And we see that, for instance, the really long lines indicate that they were affected by both outages at the same time. So what we also do, I mentioned it earlier, to really facilitate a lot of data, which also means the RIPE Atlas active measurements. So on the left-hand side, again, we have the passive tracking we did with our system before. We annotated where actually the path were going on infrastructure level. And then we see an outage, and we see like the green gets limited to just, let's say, about 10%. And then we see that there are other facilities. The path changed to other facilities, such as, in this case, DKICs or other IXPs to links. And after fixing of the outage, the path just moved back. And this is just the passive measurement. And really, to execute target traceouts, and based on the hints, we can really get a better understanding where paths go, because we cannot focus on all facilities, and especially we got trouble with tier 1 ASs, for instance. And on the right-hand side, where we did our active measurements with the RIPE Atlas system, we really see that basically a lot of path moved not to other IXPs, but also to transit. So now since we understand how our system works in general, I'd like just to highlight some of the findings we have. So one of the findings were quite surprising, because what we did is we really looked at websites and mailing lists where usually outages are reported, or at other available systems. And we found with our system we found with this verification data set, we found 159 outages, 5 years BGP data. But only 76% of the outages, or not 76% of the outages were not reported. So actually, the reporting falls behind what's actually going on. And the plot indicates a bit like the number of outages and which one were IXP outages, which one were facility outages, and we really see the red line are the reported ones. So we found that actually a lot of outages on the internet are not on the radar, so we don't really notice unless we are affected. And we also did a validation through status reports and direct feedback, so we talked to operators about outages, social media, so crowdsourced information again, and we found that we got a 90% accuracy. So each outage we really found with our system, we tried to validate. Some we simply could not validate because we could not really reach out, but 90% we could, and we really had 93% precision. So our system does not perfectly work in cases if something breaks really near such an infrastructure. So for instance, for a co-location facility, if there is a cable cut like right beside the facility, this for our system looks like the facility went down, even though actually it was on the cable outside the facility. So here we are with the service level agreements, the SLAs again. So before we heard that actually the SLAs are quite strict, but with the data we found, and since we know the duration of outages, we could really evaluate that about 70% of the failed facilities are below the actually guarantee in their uptime. So out of all facility outages we saw, 70% are 70% just don't guarantee the 3 nines anymore. And 50% of the IXPs don't guarantee their 2 nines, which they actually should according to their SLAs. And we even found that 5% of failed infrastructures are below 99.9% uptime. So actually there is a lot of room of improvement. And we see our system as a chance to really validate large scale if facilities or IXPs stick to their SLAs or violate those. So we also did try to measure the impact of the outage, and what we really see is that 56% of the affected links is in different countries than actually the facility or the IXP that experienced the outage. And we also see major changes in RTT rises. So for instance, a big IXP failed, and the issue was, one could say, okay, maybe the backup paths are as good as the default path, but what we learned here is that really if something breaks and if it's an important infrastructure, that it can be experienced by a rise in the RTT. And most of the RTT rises are about 100 milliseconds or larger than 100 milliseconds. So let me conclude. So we built a system which timely and accurately infers infrastructure level outages through passive BGP monitoring. The majority of the outages is not widely reported. So basically we find outages that are not common knowledge. And remote peering infrastructures in the interdependencies may amplify the impact of local incidents. So we saw outages that are quite far away from a remote outages in a different country on a different continent, but they still affected facilities that are hundreds and thousands of kilometers away by RTT rises or path changes. And we also provide with our system hard evidence on outages and can improve the accountability, the transparency, and the resilience strategies of network operators. Yeah, thank you, and I'm happy to take any questions. So, and if you're curious about our work and really want to understand it in detail, this paper appeared at ACM SIGCOM a couple of months ago and is available on the internet. The title is Internet Peering, Detecting Internet Infrastructure Outages in the Wild.
Thank you very much for this report. Any questions? Вопросы? Okay, then I will give you a question. So yesterday here was a report by Selectel, and they had a problem because Dietzel accepted a route that was leaked, and it was also with community that put these prefix to the black hole. And for me, it looks a little bit strange. Is Dietzel using any route maps when on export?
Yeah, the issue there is like if you have route leaks or prefix hijacks, you see a lot going on AS level. Obviously, also facility level is affected because it moves somewhere else. But those cases are not really good trackable for us, because if it's a proper hijack, you usually do it, you limit it. I mean, if you do it intentionally to 1 or 2 ASs or something like that. So it's not really that it's large scale, and we have a threshold so that we ignore 2 small events.
This issue was not about hijack, it was about route leak.
Okay.
And it was about that I was just checking that Rosprint in its ICE set, the selector is not inside. So using just regular ICE sets may be helpful. Is Dietzel using ICE sets?
Yeah, indeed. So basically this could be something to really enrich filters and make it more resilient at this point. So we didn't think about like route leaks or make it more stable, like improving the routing system basically through using this information, but we rather focused on observing what's going on. But indeed, you could transition it into a system that might help you to prevent you from such things by facilitating those information, yes.
Okay, thank you. Maybe any other questions? Okay, then thank you very much for this report.
Thank you.
It was really good, interesting.